Okay, so we were looking at resolution. So, for a long time actually most theorem proving systems were actually resolution based theorem proving systems. So, it is important in first order logic. Let us just recapitulate what we did last time and then do some examples, yeah, and then proceed to it. So, today I will just do some examples to explain the basic things, and I will not prove any theorems today. Right. Okay. So, we actually had, so the whole point of course is that what we, so resolution is a single rule, one monolithic rule of which all these are the conditions. Yeah, I mean, so these are like all the side conditions of this rule, if you like. So, essentially all this says is, first of all you should standardize the variables apart. So, you take a set of clauses in which means that their each clause is implicitly universally quantified over all the variables of the clause. And what we have from Skolom's theorem is that this set of clauses, so if I had some original formula or a set of formulae, then that this and this set of clauses is a Skolem conjunctive normal form of that original formula, let us say phi, then that original formula has a model if and only if the Skolem conjunctive normal form has a model. And of course, it is the transformation, unlike in the case of prenex normal forms and so on, the transformation from a formula phi to its Skolem conjunctive normal form is not preserved under logical equivalence. I mean, so it only preserves models, it does not preserve. So, it preserves satisfiability and unsatisfiability, but it does not preserve logical equivalence. So, the existence of so that is all. So, resolution is most often used in the form of a showing that showing unsatisfiability, that is that there are no models. Yeah, I mean that is, but however that is not just the only that is not just the only way resolution can be used. Okay, so let's assume that we have a set of clauses, set S of clauses, and since each clause is supposed to be implicitly universally quantified, that they are all universally, we assume that between two clauses we will use alpha renaming to standardize the variables apart. Okay, and so you have this, the free variables of Ci intersection the free variables of Cj is empty, and you choose any atomic predicate symbol which occurs in both which occurs in positive form in one of the clauses and negative form in another of the clauses. Yeah. So, the notion of a complementary pair as generalized from propositional logic should exist in some form here. It is what we should realize is that it is quite possible that since we are dealing with parameterized propositions, essentially your predicates are parameterized propositions, this predicate symbol could appear in positive and negative forms within the same clause itself without there being any contradiction. Yeah. And so it may also happen occur in both positive and negative forms in this clause too, but that is okay. All we are saying is that you should have at least one positive existence in one clause and a negative existence in another clause. That is, so if it is available in such a form, and if you can actually unify some subset of the positive occurrences in one clause Ci with some subset of the negative occurrences in the other clause Cj, right. I mean, so that is, so here it is Cj is Cj prime union not of P Tj prime. So, we take this PTJ prime and we are saying now you take this union and if you find essentially the most general unifier. It has to be unifiable, and if you can find this unifiable set and you take this most general unifier, then the rule essentially says that I can take this, I can remove these two clauses Ci and Cj from the set S and add a new clause which is obtained by applying this substitution. The result of unification is a substitution. If they are unifiable, then a substitution mu, which is the most general unifier, is available. So, apply this most general unifier on Ci prime union Cj prime. Notice that of course, if I had applied this this mu of this set and the mu of this set will make complementary pairs, will make sets of complementary pairs. So, so essentially they sort of cancel out each other. Yeah. So, what is left are only those which have not been unified in this from this, only those which are not in this set L. Yeah. Only those terms are left. Okay. And essentially this unified version is what is a logical consequence of Ci and Cj. And early in the game we proved a theorem which said that if you added more assumptions and so on and so forth, you can carry forward those assumptions basically. So, this the rest of S basically remains unchanged. So, at a time you take just two clauses, identify positive and negative occurrences in the two clauses, some subsets, find positive and negative occurrences such that you have an identifiable subset which is unifiable and which is non-empty, and actually calculate the unifier, yeah, which is through this unification algorithm, which of course is guaranteed to give the most general unifier. So, the rule is just this. So, this is all that you have to do, and there are no other axioms, no other proof rules. This is the only rule. So, you can think of first order in many books this is called the resolution calculus, that is it. So, this is you take the first order logic and essentially take Skolem conjunctive normal forms, take the subset Skolem conjunctive normal forms and just have one rule, that is it, one monolithic rule, and you can keep applying this rule repeatedly. So, the first thing of course is, this unified version is actually a logical, of course remember that this is a clause, yeah. So, in that sense it is implicitly universally quantified, yeah. So, it is it's a universe, it is like some kind of an application of for all elimination, but then that for all elimination also allows variables, right, and then universally generalizing on that. So, it is like an application of, firstly you have only the universal quantifier. So, if you want to get some intuition as to why there is just this one rule required, it is very simple. This unification is like a combination of two steps. You have a for all instantiation, a for all elimination, which essentially replaces the variables in Ci and Cj with some terms, and those terms are essentially the terms which give you the most general commonality between the literals in L, yeah. And then what are you doing? You are implicitly so that those terms themselves do have variables. Some variables might be new, some variables might be old. But by treating it as clauses, what you are saying is that you are implicitly applying a universal generalization, for all introduction on the variables that are present there after the substitution of mu, right. So, it is like a combination of these two, and that is, so in a certain sense it does make intuitive sense that you do not require anything else. We already have propositional resolution for other things, right. So, that is not a serious issue, the completeness there. So, our completeness will essentially involve trying to prove propositional completeness for resolution and predicate completeness, but that will come to at a later stage. Right now, it makes intuitive sense that if you keep applying universal instantiation, that means for all elimination, and then follow it up with for all introduction, you get something that is a logical consequence of your original set of formulae. Okay. So, that is what this thing is. So, let us just look at some examples. So, first remark is that of course, this is the standardizing apart. The free variables of distinct clauses must be disjoint, and the variables should be renamed if necessary, and that is equivalent to alpha renaming for bound variables. Otherwise, if you were to take, I am sorry, oh this, by the way, here there should be a negation sign here, which I have forgotten. So, if you take this set of two clauses p x and not p of f x, where f is some unary function symbol, it is clear that this set of formulae is actually unsatisfiable, right. For all instances of x that you can find, it is not guaranteed to simultaneously satisfy both of these. Yeah. Okay. But however, what will happen if you do not do a standardization apart is that any correct unification algorithm will encounter the occur check problem, right. If you remember the occurs check, this is, you cannot unify say GZZ, I mean if so you cannot unify f of x and x, for example, right. So, any correct implementation of the unification algorithm will be faced with the occurs check problem. So, which means that you will not be, even though this is unsatisfiable, and therefore, there is the equivalent of a proof by contradiction in the resolution calculus is called a refutation. We will see an example of refutation later. Yeah.
So, why was the last example, this example unsatisfiable? This is for all x p x and for all x p of f x.
No, not of p of f x.
Not of p of f x.
I am sorry. So, that there should be a negation symbol here.
This is also, I think, satisfiable.
No. Look at this. Look at it this way. Intuitively, if this second one is true, okay, then there is some value in some model. Supposing this is satisfiable, then it has some model. Okay, there is some value of which you can give to x, definitely, which makes this which makes p of f of that value a, let us say, false, which clearly contradicts this. Yeah, right. So it is not satisfiable, and what makes it unsatisfiable is just the fact that everything is universally quantified. Yeah, that's what. So, which means that you have to be able to unify it, and if you try to unify this without standardizing the variables apart, you will never actually reach the conclusion of unsatisfiability, though it is supposed to be unsatisfied. So, the first remark is that you have to actually separate out all the variables from the different clauses by doing a renaming of them. make all variables unique basically. Okay. The second thing is called factoring, and that is that it should be possible to eliminate several literals at the same time. Okay. So, that is why unlike the case of resolution in propositional logic, here we took a subset in each case, in each clause. Okay. If you do not do that, then you have some consequences. So, take something like this. If I have two clauses p x and p y, essentially they are implicitly universally quantified, right. So, essentially what this is equivalent to saying for all x, for all y, p x and p y. Yeah. And this I have standardized the variables apart, is equivalent to saying for all u, for all v, not p of u and not p of v. Now, this, if you take this set of clauses, this set of clauses has to be unsatisfiable, it cannot have a model. If it cannot have a model, but I still do a resolution such that I just choose one of, let us say I just choose this p x and not p of u to resolve on, and there are certain things which I have not mentioned here. The resulting clause C prime 1 2 that you get is called a resolvent of those two clauses. So, that C I j prime that is there is called a resolvent. Yeah. So, if I resolve it only on these two, then what will I get? The most general unifier I will be able to find is x for u or u for x. Okay. So, but C prime 1 2, oh, I am sorry. Is this right? Yeah, it is right. This, of course. So this is an OR, right? Oh yeah, each clause should be regarded as the OR of all its all the literals. Yeah. Okay. So this is essentially equivalent to for all x, for all y, p of x or p of y, and this is equivalent to for all u, for all v, not p of u or not p of v. Yeah. And that is unsatisfiable, but the result is something which essentially eliminates these two terms after unification. It leaves y and v unchanged, and so the result is for all y, for all v, p of y or not p of v, and that from that you cannot derive an empty clause. Yeah. So what we need to do if you want to prove something is unsatisfiable is to derive an empty clause, because that is like the empty OR, and the identity element of the empty OR is false, right. So, the empty clause represents contradiction or falsehood. Yeah. So, you cannot from this clause now you cannot derive the empty clause, and that is because you have done an incomplete kind of unification. Yeah. So, actually the only way therefore is to actually do a full unification here, which for example x for u and y for v, and then you automatically get the empty clause, right. Okay. So, factoring is something that you do. Okay, so let's look at, so there are certain subtle issues with resolution which we need to worry about. So, here let us look at this. So, let us take a simple example. So, here is something that I just picked it up from modal logic, but we are not going to do modal logic. So, essentially, take a binary relation. So, our models, let us say, are some, either you can think of them as some kind of graphs or some kind of just relations on sets. Yeah. So, you are looking at some binary relation which is reflexive, and it is Euclidean. Okay, Euclideanness is a property of some modal logic, but let us not worry about it. It is possible to bring it down to just this notion of relation. Yeah? So, Euclideanness just says that if x y belongs to a relation and x z belongs to a relation, then y z also belongs to the relation. So, it is closed under that. Euclidean, I think, is because of some, they form some kind of a triangle, right. I mean, so it is a, it is the qualitative notion of a triangle inequality kind of thing. Yeah, that is why the name comes. Otherwise, the name has otherwise no significance. But since it is a technical name, we might as well use it. Yeah. Okay. So, basically, what you are saying is that then it is also symmetric, and actually this is quite obvious. Yeah. Right. But we have to look at. So, let us look at how to go about proving this. So, so this is the notion of symmetry, right. For all x y, p x y implies p y x. Remember that it does not matter if I replace this arrow by a double arrow, by a biconditional, because with this universal quantifier the two things are equivalent. I mean so this is an example. I mean, this is an example of two different first order logic statements being logically equivalent, even though they're not like propositional tautologies, and we cannot, in propositions you cannot easily replace this arrow by the biconditional. But the presence of this universal quantifier and the notions of validity and so on and so forth make it equivalent. But anyway, it is easier to live with just this single arrow. So, let us go with that. So we rename bound variables and convert to Skolem conjunctive normal form. But that in this particular case, this is the reflexivity property. So, it is just Pxx, that is it, there is nothing else to it. In the second case, what you have therefore is that essentially I am going to write it as for all u, for all y, p of u v, for all u, for all v, p of u v arrow p of v u, right, which is not of p of u v or p of v u, yeah, which is what I get, here. Hey, I am sorry, this is the Euclideanness, yeah, I am sorry, Euclideanness, right. So, for all u v w, that is what I should get, for all u v w not p of u v, comma not p of u w, comma p of v w, that is not p of u v, not p of u w, p of v w. Yeah. Okay. If I look now, we have only one atomic symbol here, yeah, and you find some most general unifier. It is clear that, okay, so look at it, in this class C2 there are both positive and negative occurrences of the same atomic predicate symbol. Okay. In the class C1 there is only a positive occurrence of the predicate symbol P, which means that this anyway has to be a candidate for resolution, there is no other go. Yeah. And if I take positive symbols from here, positive occurrences of P from here, then I have to take some negative occurrences of P from here, right. Of course, I could have taken this, or I could have taken this, or I could have taken both. Yeah. But supposing supposing I decide to resolve these two, okay, and supposing I decide to take all of them, then what I can do is I can actually take x for u, x for w, y for v. That is one general unifier. Yeah. So, the process of unifying these two, I can actually define this, and that yields just this. So, this is equivalent to essentially for all x y, p of x y arrow p of y x. Yeah, is that fine? So, I have chosen this unifier. That's a strange thing, you know. That's, I mean, could I have just chosen x for u and x for w without a y for v? Could I have chosen x for u, x for w and x for v? So, if I had chosen x for u, x for w, x for v, that would be less general than this. Okay. Supposing, okay, actually x for u, x for w alone would be more general than x for u, x for w, y for v. Yeah, because I am making the least number of commitments. Supposing we had done that, then what would have happened is, if I had just taken x for u, x for w, then I would have got essentially not p x for u. So, my mu c 2 basically. So, I choose my mu to be just x for u and x for w. Yeah. Then what I would have got is not p x v and not p x x p v x, right. That is what I would have got for. So, this would be mu c 2. Yeah. Mu c 1 of course continues to remain just p x x. Yeah. And the result of resolving would have essentially gotten rid of these two and would have given me not p x v p x v, and actually this would be the most general. V x, I am sorry. Actually this would be the most general, right. But anyway, so this is actually less general than that. So the unification algorithm would have just done this. It would have just given you this, which is equally good. Yeah, which is what is good. But it is just that I wanted to show that it is sometimes possible to choose some unifier which is not necessarily the most general and still give you some logical consequence. But that is dangerous sometimes. Yeah, and so the other way and somewhat more direct way is to do what is known as a refutation. So, a refutation is essentially a proof by contradiction, right. So, you assume the negation of the conclusion that you are going to take. Okay. So, in this case, so let us do the same example. So, we have the same thing that this binary relation is reflexive and Euclidean, and you have to prove symmetry, and this is the formula, this is the representation of symmetry, which of course whose negation will convert all the universal quantifiers to existential quantifiers. Okay. So, which means you will get there exists u v p of u v and not of p v u. Yeah. Which on Skolemization means that I will replace first one existential quantifier by a new function symbol, which is a function of all the universal quantifiers which preceded it. Of course, there are no universal quantifiers which precede there exist. So, what you get is a constant a, and having replaced that by the constant a, what you would have got therefore is there exists a v p a v, where a is the constant and not p v a. Yeah? And a further Skolemization would only replace this v by a new constant, because there are no universal quantifiers before it, and that is the constant b. So, basically you will get this p a b and not p b a. Yeah? p a b and not p b a is actually two clauses, right. So, which I will call C 3 and C 4. Right. Now, what you can do is you can actually just add the C 3 and C 4 to those two clauses C 1 and C 2. Make sure their variables are anyway have been standardized apart, and go through and apply the resolution rule. Yeah. So, when you do that, you get this. Okay. Here I have given some general unifier, and this is not necessarily the most general, but that is okay. By the way, this y for v can be removed, it does not matter, and actually your unification algorithm will give you only x for u and x for w. Yeah. And now what will happen is that you can follow essentially the same proof as this, and but now what the refutation gives you is it gives you an empty clause after another unification, where you have to, in order to be able to unify this PAB or not PBA with this not PXY PYX, what you have to do is you need to give you have to notice that it is completely symmetric. So, I could have either chosen A for x and B for y, or I could have chosen A for y and B for x. It is completely symmetric, but depending on which one you choose, you will be resolving against two different clauses. But the effect is that you would have derived an empty clause. It does not matter what other clauses are hanging around, but you would have derived an empty clause. Yeah? And the fact that you can derive an empty clause essentially means that you proved a contradiction, right. But normally any refutation procedure would not actually follow this path. So, the path here I have followed is that of this previous proof. It would actually start with these constants, so that you try to get your contradictions as early as possible, right. So, here is the first theta 1, which just does B for V and an A for W, and it resolves this P V W against this clause not P of B A, does this substitution and you get this whole thing. Then you got this P A B and you got this not P U B, not P U A. So, one possibility is to just do an A for U and get this P of x x and not P of A A, which of course derives the empty clause with an A for x. Yeah. And so it is possible to play around with various kinds of unifiers. Some of them will give you the result, but if they are not most general, there is a problem. There might be a problem with what you consider to be logical consequence. So, that logical consequence often is guaranteed to hold only if you take the most general unifier. In this particular case, it was lucky with this y for v, because it was just a renaming of a variable, it did not matter. but as you can see here, this example clearly shows that if you did not take the most general unifier and if you did not unify as many literals as possible, the goal should not be to eliminate as many clauses as many literals as possible, but the goal should be to get the most general unifier and eliminate all that unifier can eliminate. Yeah. So, and once you do that, you can actually you will actually get a fairly automated and deterministic result. So this is this is the alternative proof with the clauses C3 and C4. Okay, let's just do another example. So here's a set, okay, which essentially represents this is the example that I pointed out last time, which we did not do. Yeah. So if you have transitivity and symmetry of a relation, then you have you can derive this. Yeah. So let's take a predicate Q. Let's just go over it systematically. This one is the transitivity property, which says that for all x y z, q x y and q y z, then q x z. Yeah, which in clausal form is these three literals. Yeah, not q x y, not q y z, q x z. You take symmetry, we have already seen symmetry. So, and of course, I have to standardize variables apart. So, I take two new variables u and v, and I get not q u v, q v u. A logical consequence of these two is something which says for all x y z, q x y and q x z, then q y z. So, there is a permutation of the bound variables, right. So, that is what this is. Yeah, right. Okay. So, of course, so what you do is you just find the most general unifier. One possible way is to actually take z for u and y for v and resolve against this substitution. And I did not try to resolve, I did not try to eliminate any more variables, I did not try to eliminate any more clauses. I just took one simple most general unifier, and the result is this C prime 1 2, which essentially is this logical consequence. Yeah, right. So, so there are some essentially certain subtle issues to be resolved. One is how to make resolution completely deterministic. Part of the way of making resolution completely deterministic is to just limit yourself to the most general unifier. So, that is crucial in some sense. But then there is this question of, are you guaranteed whatever most general unifier you get, is it guaranteed that your refutation procedure will always work? By the way, logical consequence is a slightly non-deterministic process. Refutation is more deterministic. So, your most general unification and refutation together give you a more deterministic way of approaching the problem of proof. Yeah. And of course, there is this question of is it complete? Can you actually prove everything that you can prove in any other complete system? Yeah. Whereas, on the other hand, compared to all these other systems like Hilbert style systems and natural deduction systems and so on, this resolution system has a potential to become extremely deterministic, and therefore, you do not there is of course a problem that with all theorem proving procedures is that the reasoning mechanisms becomes counterintuitive. I mean, it's not easy to reconcile those procedures with your normal methods of reasoning, right. That there is that problem, but besides that, essentially it gives you a fairly deterministic method which can therefore be automated. So instead of an interactive theorem prover where the user supplies essential intuition to proving the theorem, that is what would happen. Supposing you take a Hilbert style proof system or a natural deduction proof system, every rule in it is decidable. That means, given the patterns of the hypothesis and the pattern of the conclusion, it is possible by an algorithm to decide whether it is a correct application of the rule or not. If you have a finite set of rules, you can go further. Given any set of patterns and another pattern, you can determine by an algorithm, exhaustively checking out all the rule patterns, which rule was applied in order to obtain it, or whether that is an application of a rule at all or not. You can give a deterministic answer, right. But you cannot proceed to do the proof in a deterministic fashion. For example, you cannot run the theorem prover to just go and find a proof, right, which you can do with something like resolution. Yeah. So, what any resolution theorem prover would do therefore is, you give it a set of formulas to prove you give it some logical consequence to prove. So, essentially it will do a negation, it will do a Skolem conjunctive normal form, it will do standardizing apart, all those are simple algorithms which can be done, and then it will actually rename all the variables anew. It will generate temporary names for all the variables, maintain a table of correspondence, and then it will run the and it will essentially call unification, which will give it some unifier, and it will keep resolving against them. So, actually what it will do is, it will do what is known as a linear resolution, which is not very important, but basically what is important is to be able to see that there exists positive and negative occurrences of some atom in two different clauses, and that they are unifiable. So, basically you can exhaustively look at all that, and you can find a unifier, do the substitution, and then continue with to find positive and negative occurrences of some other atom maybe, and again do the resolution. And so, this process can be done in a completely batch mode without any user intervention, whereas any proof which involves natural deduction or a Hilbert style system would require user interaction, because the user will have to provide an essential proof technique, right, which is not deterministic. For example, we know that in the Hilbert style system, one of the exercises somewhere actually showed that for every proof which was direct, that means you assumed only all the assumptions and tried to get the conclusion from the assumptions for every direct proof, there is also a proof by contradiction, which is equally correct. That is as far as larger proof techniques are concerned, but between these two there are a huge number of variations possible. I can start off with a direct proof, somewhere in the middle I make an assumption to derive a small contradiction, and then I continue with the direct proof, or I make more and more, I define essentially within that proof, I define a series of lemmas which are all proven by contradiction, let us say. So, there are all these variations for which any theorem prover would require guidance, it cannot do it by itself. Whereas, this resolution and actually the tableau method, I mean we have to do the tableau method also for first order logic, they have a genuine potential for essentially feeding the theorem to be proved to the system in a batch mode. Just give it to the system and let it crunch it out. It will crunch it out with an answer finally. Either it could do it or it cannot do it. And that is essentially automatic, really automatic theorem proving. Otherwise, most theorem provers which use other systems are not automatic, they are interactive theorem provers. So, at every now and then the user has to give some essential intuition to the system before it can prove. Yeah. So, I will try to do the soundness and completeness of resolution tomorrow and maybe on Friday. I will stop here today. I do not have anything more really to say. I just thought I will do some examples today to show that there are certain subtleties with resolution. Yeah. Okay.